Welcome to lecture number 6 in our lecture series on quantum field theory. So today we are attacking one more tool that we want in our toolbox once we go into field theories. And I want to develop those tools while we're still in quantum mechanics. Right? So the one we're tackling today is called the Wick Rotation. So we are talking about what is called the Euclidean time. Consider the following integral, which has appeared already a few times in a very similar form to this one. So that's essentially a Gaussian integral, but you have this imaginary part here. So it's integral over this imaginary Gaussian. Right? So we know that this integral makes sense if we take either alpha or x to be slightly imaginary, so that we can then see in which conditions this integral actually converges, right? You have if one of these is slightly imaginary, you have an integral that is exponential of minus a real number that goes to zero in the proper limit, right? And this converges. So already there is behind that the idea that this integral is defined by its analytical continuation, right? So you need to take these variables to be continued analytically to the complex plane in order to calculate this integral. Right? And this integral is showing up all the time for us because essentially that's what we know how to do, right? So even if I'm all the time I'm getting exponentials of minus I the action, right? And the action can usually be written, right, as an approximation where I take the action calculated in the extreme of the action plus a quadratic part around that minimum. That's why I'm calling delta Q. Delta Q is the distance to this Q, right? Sij delta Q of j plus whatever, right? Which can be cubic, quartic, higher order powers in Q. Right? So that's an approximation that you can take if you're talking about states that are very close to the classical one, right? If you're doing perturbation around the classical trajectory for the system, right? In the cases where this was not there, right, and this cubic term was not there, then this approximation is perfect. This is called the saddle point approximation. And of course, in the cases where we already didn't have cubic terms, this was perfect. But even when it is not perfect, you see, we'll do that many times in the course, we can then treat this part that we disregarded when we use this perturbatively. And so this will show up every time. When I take the saddle point approximation and put here, I get a quadratic integral, a Gaussian integral that looks a lot like that one. And now I want to look the analytical continuation that I do here in a different way, right? That will allow us to make interesting connections to statistical mechanics and also understand one or two things about that process with the boundary conditions and the projection into the vacuum of the system that we saw last lecture a little bit better. So let's see how can we approach this. Let's think in terms of an arbitrary quantized system defined by a Hamiltonian, and I'm working with this eigenstates of that Hamiltonian, whatever that may be, right? So not exactly concerned about what the system is, and only that I have a certain set of discretized energies and the states associated to each energy. And I am assuming for now that the energy is positive. Right? Of course, these states are normalized, and I have a completeness relation for them, which we'll use a lot, right? So for that system, any transition amplitude, again in the language we have been using a lot here recently, can be written like that, right? Again, I'm taking these moving frame states, Heisenberg picture states, and I can write them in terms of Schrödinger picture states as following, right? That's minus I H T prime minus T Q, and now in the Schrödinger picture, right? So for now, because of it will be interesting to keep H bar around, I'll get back our H bar. So I have been using natural units, so H bar equal 1 everywhere. For the following, I'll be explicitly worrying about where H bar is. So I write it explicitly. So now I will introduce some of these completeness relations here and there, right, which allow me to write this expression in terms of two sums, N and M, of these eigenstates of energy. So I got Q prime, I'm inserting the first completeness relation here, and exponential of minus I H over H bar, T prime minus T, M Q, right? Just inserting those states. Of course, these are eigenstates of the Hamiltonian, so I can replace the operator by the energy acting on one of those. I'll choose this to be M, say, but then of course once I remove that exponential from this bracket here, the bracket itself is normalized, so I get a Kronecker delta here, which then I can use to make one of those sums and make N equal M, right, including here in the energy. So that allows me to write that same expression as this just one sum over N of Q prime, this part, Q prime N, and then M is equal to N, so it becomes again N Q, and then the exponential, which is minus I energy over H bar T prime minus T. And then of course these guys are just the wave functions. Which then allow me to put this in the form which is convenient for me. Which is this one. Giving me the transition amplitude in this language. So far so good, right? So now just looking at this, we see, I mean, the time is real, right? So this is a real variable, but we see that this function is analytical for T prime minus T, right? Even in the complex plane. So we can continue that for analytical for complex time. So just baptize this delta T. I'm actually complicated. I could have put T equals 0 and T prime just T, but since I started with T prime minus T, that's the only variable that really matters, is the distance, right? I don't have two different ones, right? But I'll continue this analytically and make the following rotation in the complex plane. I'll take delta t and substitute it for minus e t Euclidean. The reason I'm calling this an Euclidean time will be clearer later, right? For now, it's just changing variables, right? And that is what called a Wick rotation. I'm changing my variables here by rotating to the complex plane, and the direction of this rotation is chosen to keep an important property of the evolution operator, that is that it is bounded. It is a bounded operator, and it's not, I mean, the moment I extend this evolution operator here, which is exponential of minus I h over h bar delta t, once I extend this into the complex plane, this will not be unitary anymore, but I still want it to be bounded, in the sense that if I calculate psi u dagger u psi, this will be smaller than some finite number psi, which is important to define proper quantum mechanics, right? So I need these operators to be bounded in Hilbert space. The problem is, let me write these as using that completeness relation I used above. This will be just energy over h square delta t n, right? I could I inserted the identity here and acted with the Hamiltonian on this state, right? And then when I do the analytic continuation of delta t, this becomes just the sum exponential of minus I energy over h square h bar real part of delta t times the exponential of energy over h bar, the imaginary part of delta t. And this is the operator. So it's clear that if I want this property to be true for a finite c, right, I have to keep this exponential under control. Otherwise, for when delta t goes for large times, this operator keeps getting a diverging exponential here that will grow, and this operator will not be bounded. The condition is then that the imaginary part of delta must be smaller than 0, because if this is negative, then this exponential converges and this guy can be bounded. So if I put that on the complex plane, the condition I'm finding here is that, let me put here, that's the real part of delta t, that's the imaginary part of delta t, and the condition I'm finding here is that if I start with delta t, which is positive, right, energy is positive by definition here. I'm assuming this Hamiltonian is bounded from below. I have a discrete spectra of energies, and there's a minimum, which I can take to be 0, right? I can always rescale to get that energy into 0. So what I'm saying here is I take delta t positive, then this rotation needs to be into that direction. And of course, I took a rotation of 90 degrees. In this region, I'm declaring a not good region because this guy becomes unbounded, right? No good. And with those identifications, I mean this identification, this will be minus the real part of t, right? So the axis of positivity goes down, and this is the same as the imaginary part of t Euclidean, right? With this relation up here. Okay, So what happens to the expression we had before if we use this substitution? I'm talking about this one. Now I'll take this and make the Wick rotation. So now of course I exchanged delta t, which was t prime minus t by te. So now in Euclidean time, this stays the same. I forgot a psi star here, which was actually missing up there. Yeah, this is psi star. This is psi star. Right? If I was in class, I could accuse the students of not noticing when I was doing it. Now it's all my fault. So psi star, and here of course that was delta t, and minus I delta t is by this rotation here, minus I delta t is just te minus te. So I stay with minus te right here. So this is the propagator in the Euclidean time. Now, suppose I, instead of, so this is a transition from one point into another, right? Suppose now, instead of calculating this, what I did was to calculate the same object, but for q equal to q prime. That means I just exchange q prime by q here. And I also integrate in q. We are just in one dimension here, but imagine we were in two just for the sake of the drawing. The moment I make q prime equal prime q, I'm talking now about closed paths, right? I start and I end at the same point. In one dimension, this would look like a really strange drawing, right? But also, as I integrate in Q, I'm not keeping this point fixed anymore. I'm integrating it all over space. So I'm really talking now about all closed paths in this space, right? When I do that, I will also do something to avoid confusion later, which is to call TE tau, right? So you better keep in mind that both TE and tau are Euclidean, in the sense that I'm doing this Wick rotation to get to them, but tau is is the length in this Euclidean time of a closed path. So tau will be like a period or a length of a closed interval, and TE I'll use when it's open, right? This distinction will be important later, and I want to keep it, beside being both of them being Euclidean, right? So now if I substitute this in these expressions up here, I can use, now that I have the integral in Q, I can use the integral in Q of these, right? We know that the integral in Q, and of course now Q prime is equal to Q, so here I just have the module of psi n Q square, and we know this is 1, right? Because I'm assuming these wave functions are normalized. So if I include this integral here and make Q prime equal Q, I can use this and write this just as the sum over n of the exponential of minus tau over h bar en. which is the same as, I'm just taking the eigenvalues here, right? So this is the same as the trace over all these states that I define here, the n, right, of the operator, the Hamiltonian operator. But now we notice that this here, right, or even this is the partition function, right? This is, if I identify this number right here as the thermodynamic beta, right, you identify exactly the partition function for statistical mechanics system, right? And that's a bit curious, right? So because I started talking about a quantum mechanics system that can be characterized by just one position, so this, whatever the energies are, the Hamiltonian is, this is one particle states, right? It's characterized by the position of something, right there. And then I did all the possible closed paths that could be, one could, all the possible trajectories, closed trajectories of length tau, right? That you could make in this with this particle, and I got a something that is amazingly similar to a statistical mechanics system, right? In fact, you could identify what would be the temperature here. If I'm calling this beta, right? The temperature would be something like that. I'll call these T quantum, right? Because it's analog, right? I know this is not a quantum mechanics system in contact with a heat bath. It's just one particle, right? And still there's something equivalent to a temperature here. This is the Boltzmann constant, by the way, which actually in natural units is also one, right? But for now we're carrying both constants here because it's important to see the relations here. So that's curious, and we want to understand it better. We want to delve deeper into these analogy between systems that are in principle very different, right? So just keep in mind what is happening is that I'm taking a path integral in a closed trajectory, all of them, right? And somehow the length of these trajectories, right, in time, but you see that this Euclidean time is more similar to a distance than in space than a distance in time, right? And there is this relation, right, that I could write like this between the length of the quantum mechanical system and the temperature of the statistical mechanics system, and these two are analog to each other by the partition function. Actually, that's why we keep calling this generating functional z. You see that's because of the analogies between z and the generating functional and the partition function of statistical mechanics that we call both of them z. So let's move forward and think now about specific Lagrangian, right? One that we like a lot. So let's take some more specific type of Lagrangian, right? Which can be written as a kinetic but plus potential term, right? In this case, we know the action, right? We have written that a couple of times already. It's just now be very careful with the notation here. So I'm going between t and t prime, This is just an integration variable. I mean, this is before I do the Wick rotation. And this is half del Q del T prime prime. Oops, too many primes. Square minus phi of Q. The first thing I can do here is just first a simple translation, right? To remove this t and exchange this for integral then from t to delta t, right? This is just translating this variable, changes nothing into the integral. And then I want to do the Wick rotation itself, which means I'll do a change of variables from this t prime and the limits of integration into the imaginary continuation, right? So I'll use t Euclidean to mean I t prime prime there, the variable of integration. Of course, I'm just using the same rotation I defined before, right? This I is on the other side. And then of course this d t prime prime will be minus I d t e, and the limit of integration will become I delta t, right? When t prime prime is delta t, te will be I delta t, which of course is tau, because remember I'm using tau to indicate the range I'm integrating to, and te to indicate the variable. My integral now becomes I integral from 0 to I delta t. The integration measure here comes d t e, and now I have to deal with the Lagrangian itself, right? So this is half. The function, right, this q, it was originally a q of t prime prime, right? Now it will change to a q of minus I t Euclidean, right? And I will baptize these just q e t e. So however these imaginary numbers is being absorbed in the function changes the shape of this function, and of course it becomes this new one, which is the q Euclidean, right? So here I have del q, oops, del q e, del minus I t e square, and minus v of q Euclidean. Again, the same definition, right? This defines this function here. So first thing to notice, this is tau, right? So this is just tau, which is also the same as using this h bar beta, right? So that depends on, I use mostly h bar beta for it, but remember beta is just identified by the relation above with tau. And this part here I'll just call minus the Euclidean action, which now depends on the Euclidean position, right? So instead of here I have is, and I'm calling this minus s because again this is how actions show in statistical mechanics, and I want to explore that relation. So now just simplify all the factors of I here and write these in a more explicit way. So SE QE is, so here these two guys cancel each other. There'll be a minus coming from here. There's a minus I square here, which makes the whole thing negative. I can take a minus out, right? these two terms now share a same minus sign that goes outside, and this is the sign, so this guy is positive, right? So I end up with an integral from 0 to h bar beta dt Euclidean of half del QE del TE square plus VQE, which is actually, if you pay attention to it, this is kinetic plus potential energy. This is the total energy of the system. So you see the Euclidean action has the classical Hamiltonian of the system here. I have just the energy, the total energy there, right? And of course, I sometimes just write these like this in terms of Lagrangian, Euclidean Lagrangian too. I'm just defining a bunch of Euclidean quantities, right? So now if I want the partition function, right, all I have to do is demand that the trajectory is closed. I need to put in the boundaries of path integral that where I use this guy, right? I use this on a path integral, right? Exponential of this. I just have to demand that the 2 points are the same, right? That's why I'm already implying this by using tau. And then I'll obtain the following, right? This z of beta, which I already shown above, that is the trace. So I have shown these. Which I can substitute, right, tau by h bar beta. H bar goes away. This is just beta h, right? Of course, that's how I defining beta in this case, right? This guy goes here. And now I'm saying that is also another way of obtaining the same quantity as I have shown here, right? I get to the same quantity, right? But now I'm writing this as a path integral, right? Because I know I can do that. I know I can turn this transition amplitude into a path integral, and the path integral I get is actually this one, with the condition that this is cyclic. So I'm integrating over all closed paths of length tau, right? And I already did the rotation to Euclidean time of the action. That was what I was doing here, right? Just to be clear, I have shown that this can be obtained through a path integral right here. Okay? The moment I'm saying this is the partition function of a statistical mechanics system, I write it like this. I can get here. That's what I'm showing this far, right? And this I know how to put it in terms of a path integral. I just now rotating it to Euclidean time and closing of the path, integrating over all paths. So there's one more integral here in the path integral. I usually have infinite amount of integrals inside the path integral, but extremes are fixed. Now I just made the two extremes the same point, and it's not fixed anymore. So I have one more integral, but that poses no difficulty. I could do the same derivation I did before for the path integral with those points also being integrated over. And this is known as the Feynman-Kac formula. And this relation is interesting because first it allows us to now use path integrals in statistical mechanics, which is unexpected, right? I just have to remove this h bar from here, substituting it by temperature and Boltzmann constant, and right, it's easy. But again, but still, it shows us again the importance of this quantity, right? This is the analog in statistical mechanics of our generating functional, and we know in statistical mechanics how much of these relevant quantities you can derive just knowing the partition function, right? Once you know the partition function, you can get many thermodynamic state variables out of it, right? So we see the analogy between these two quantities. You have the generating functional in quantum mechanics and the partition function in statistical mechanics that play kind of the same role. Now let's complicate things a bit further, right? Let's now think of a quantum particle which is really in contact with a thermal bath at temperature T, right? Don't confuse this T with the TQ we had before. This TQ we had before was analog to this length. It was actually related to h square, right? H bar. This is a real temperature. Now I have a quantum system in contact with a quantum particle in contact with a thermal bath at temperature T. We know that the quantum mechanics of this system is given by this density matrix, right? And the statistical mechanics of quantum systems set by this density matrix, which is defined as 1 over z. This is a normalization, but I'll soon prove that the z that shows up here is the same we have been using before, right? And the exponential of minus beta h, right? Where beta is the Boltzmann factor, right? That's kBT, this temperature, right? The real temperature of a bath. And this encodes probabilities, right? In fact, the probability of finding the particle in the state with energy En is given by this, right? So this density matrix is encoding all these probabilities, and there's a normalization condition for the matrix, for the density matrix, which is that the trace of the density matrix is 1, which of course implies, if I use this, that z of beta is the trace of the exponential of minus beta h. Right? Just take the trace on both sides here. Z goes out of the trace, and you get the same definition for z that I got up here. Right? So this is really, the normalization here is really 1 over the partition function. And then if I want to calculate the expectation value of any operator in this system, right? Say I have an operator O at temperature beta, right? This is just the trace of the product of the density matrix with the operator, right? So this will be the expectation value of the operator, right? The trace over all states. Again, that's why I see states here is the same state, and that's what the trace means in this case. Right? What I want to show here is the relation of these with the Euclidean time, right? So the evolution of a quantum mechanical system is again just given by this, right? By this operator in normal time, let's say Minkowski time. I'll soon make clear why this Minkowski and Euclidean. If I take this through a Wick rotation, right? This becomes the U of minus I tau. Again, I'm thinking of closed borders, that's why I'm using tau, right? So now there's a tau is equal h bar beta, but this beta is with this temperature, right? And this is just exponential of minus tau over h bar h, right? The Wick rotation here. And this is exponential minus beta h. Let me put a q on this beta here to indicate this, right? That this beta q is 1 over Boltzmann constant T q. That means the density matrix can be written in terms of this evolution operator, right? Because in fact that's exactly what shows up here for different temperatures, of course. This is for a real temperature of the system, and this is for an analog, right? But if I want to go into that direction, right, I have a real system and I want to connect it to an analog, I can identify those two temperatures, right, and write it like this, right, where Z is now minus I tau, right? So both the partition function and the density matrix are given by this evolution of the quantum states, but on Euclidean time, right? Making this duality between these two theories. So to make things clear, what I'm saying here is that I have very similar descriptions for two apparently different systems. One is a quantum particle in a thermal bath at temperature T. Another one is a quantum particle in vacuum. So there's no temperature at all. But I'm treating this second one in imaginary time. I'm doing a Wick rotation. So this guy is characterized by a density matrix. Or if you will, partition function. These are operators. And beta is 1 over temperature, right? And this guy is described by this time evolution. But if I go to imaginary time, I just get this, which is actually the same function that shows up here and here, as long as I set this length I'm calculating here to match that real temperature there, right? So this guy is h bar beta, which is h bar over Boltzmann constant, this temperature. And so if I do this, so essentially I choose the length I'm evolving through in the time evolution operator, then I get the same, exactly the same exponential. So both systems are controlled by the same function here, this evolution in imaginary time. Systems that could be very different. But there's one more thing we can see here, which is very interesting. And it shows up when we think a little bit about this imaginary time, or Euclidean time, as I have been calling it, when I think how it behaves inside metric, right? So I'm using this convention for our metric. It's just mostly minus convention of particle physicists. It's not very convenient for Wick rotations, but you can use it anyway, right? And in this convention, the time space-time interval is this, right? I don't care how many dimensions we have in spatial coordinates, it will be like this anyway, right? When I do the Wick rotation, what happens here? I have to put two i's here. I change the sign of the time interval, right? And I can define a Euclidean space-time distance. I put a minus here because an overall sign on this interval means nothing, right? And this is just Euclidean plus the other coordinates, right? Square. Which is now you see why I'm calling these Euclidean times, because this is really Euclidean distance, right, with one extra dimension. So if here I was on Rn space, right, if I had n space coordinates, now I have n plus 1 Euclidean metric, right, in these variables. So see that really time has gone away. This guy behaves as a distance, as a space, right? And then when we think this guy as a distance, it changes a little bit how we see the discretization I made to get the path integral. To see how, let's think of the Euclidean action I wrote a few minutes ago. It was just the integral in Euclidean time of the kinetic energy here plus potential energy, and let's now specialize these to our favorite system, which is the harmonic oscillator. And let's see what happens here, right? When I make the slicing needed for the path integral, right? What I do is to get to that expression, I discretize time, right? So what I had was something like initial time, Euclidean, right? Which I'm calling 0 here. I final one, TEN, which was tau, and I have many pieces in the middle here, right? So that any intermediate Euclidean time is just J times epsilon. Epsilon is the size of any of these spaces, right? And the Euclidean position at time AJ, I'll just name QJ to save us some notation, right? That means that my partition function or my generating function or any quantity that I calculate will be the path integral in Euclidean time now of the exponential of minus 1 over h square, h bar of that action. 0 to tau dte of this. Well, let me write it again. I'll put it in a better way. QE dot square, right, over 2 plus half this one, omega square QE square. For those of you wondering about this 1 over h bar here, this is just, we never had this, right? We just had the exponential of minus I action, and now it's becoming the exponential of minus the Euclidean action, right? But of course, this has dimensions of action, and h bar has dimensions of action too. It was missing because we made h bar equal 1, right? So it should be there all along. Since now I'm keeping track of h bar, I brought it back, right? So it should be there all along. And of course, if I want to do the path integral through this discretization, which was the definition of it, right? What appears is the product of many integral in these qj's here, and the exponential becomes this integral becomes a sum over j. This interval becomes epsilon, and in here we have half of qj plus 1 minus qj square over 2, sorry, over epsilon, this is the derivative, plus half omega square qj square. Right? Which is again a partition function, right? Because now I don't have any imaginary numbers here. It all become real functions in terms of these variables, and this is actually a partition function, right? I have the sum over all configurations, right? This is what the path integral does. I'm integrating over all these variables, so I'm taking into account all the possible configurations qi. Any set of qi's is a different configuration, right? This I can again identify as 1 over, I'll call this TS, right? It's yet another analogy that I'm making here. We'll soon see what temperature is this, but I can identify this as a temperature, right? And this is the total energy of the system. So you see there's a coupling term here between near neighbors that make it's smaller if they are aligned, I mean close to each other, and there is the energy of a harmonic oscillator too, right? You have to be careful about calling this a kinetic energy, because as we see here, there's no time anymore. I have been calling it kinetic energy by analogy, but this is really a coupling between neighbors, and this is the potential energy of a classical oscillator, right? So what we're seeing here is that this is what is being described here is really this lattice of a system of quote-unquote oscillators. Remember, there's no kinetic energy, but what you're seeing here is really this lattice that has many, I'll indicate like that, So many particles here set in a lattice, and this distance here is really the Euclidean time, right? And there's a piece of the energy that is given by their distance, right? Q is how far they are from this axis. They have this coordinate, right? But there's also another term that I indicate with this green line here that couples near neighbors, right? Only the nearest neighbors, right? And of course you're summing over all the configurations, and this is giving the partition function for the system. So in a sense, one oscillator in Minkowski time is being rotated into a lattice of many bodies with this coupling between neighbors in Euclidean space. All of that in equilibrium with a temperature, this temperature here, right? Which is again an analogy between two very different systems, which are related to each other by this Wick rotation. In summary, what we're seeing is that if I take just one harmonic oscillator and go to imaginary time, I can use it. I mean, this is analogous to a chain of these coupled classical oscillators, right? And in the same way, the thermal oscillations on this side will influence, right? You have for each temperature different configurations of these coupled classical objects here are possible at different temperatures. Here the temperature essentially is controlled by h bar. It's not by accident that we had h bar here when we are coming from the quantum side of this duality here, and we have to identify the temperature in the same place where h bar is here, because h bar is the one controlling the fluctuations on the quantum side, and the temperature is the one controlling the oscillations on the classical side, right? And this I call that, now it's clear why I call this TS, because this is really a system of classical objects, right? On the quantum side, you have just 1 degree of freedom, it's just one particle, one oscillator, and you end up with many degrees of freedom on the classical side. But also we have just seen that this oscillator in Euclidean time is a way to describe a finite temperature quantum system. If I take this oscillator and put it in a heat bath, one way of describing this quantum system is going to Euclidean time, right? And then I have this temperature, which is given by the length of this Euclidean time I'm considering, right? And this is, again, is equivalent to something on this classical system. It's easy to see what, right? The length of the chain, right? When I made this discretization, right, I took the total length of the chain to be tau. So even the temperature on this side, if I remember that this particle in imaginary time is really the same as a quantum system in contact with a thermal bath, right? There's also analogous on this side, which is the length of the chain, which I can take to infinity. If I take the length of the chain to infinity, I take the temperature of the quantum system to 0, and I go back to a particle in vacuum. We use this idea a lot. So if we want to do path integrals in Euclidean time, which many times is useful, right? But then we want to go to a system without a temperature. I mean, I'm talking about particles in a vacuum, for instance. I can do that in Euclidean time and then take this length to infinity. That will make the temperature go to 0. And if I don't want the temperature to go to 0, suppose I'm treating quantum field theory at finite temperature, then I can keep this length finite which will give me a temperature on the Minkowski, on the quantum field theory, right? So then I have no time, because I'm always, when I'm using this, I'm always treating systems in equilibrium with a temperature. So there's no evolution in time for the system. That's why I can do this without a time, right? The Euclidean time serves really as a proxy for temperature. This is all very interesting, but let's see how we can turn this to our favor. How can we use it in a course where we're actually interested in calculating almost everything? Will you look at in this course, it's at zero temperature, I mean the vacuum. So let's see how that can work for us. Right? So the first thing to notice is how operators, how do I get expectation values of operators, right? So if I take an operator A of Q, so that any operator that depends on the coordinates, which are operators themselves, right? And look at the finite temperature. So now I have a quantum mechanics at finite temperature T, right? The expectation value of the operator will be given, as we know, by this, right? As I have just shown. I just have to calculate this at Euclidean time, the Euclidean space, and this is the trace of the density matrix, density matrix times the operator, which then I can write this density matrix explicitly. I get a factor of 1 over z outside times the trace of the exponential minus beta h a of QE. And of course, this is the time, the evolution in Euclidean times. That I named before. And this guy is also the trace of the evolution in these Euclidean times, right? Which means I can write this as the trace of U E tau A Q E over trace U E of tau. Right? The main advantage we have now is that we know how to calculate these two things in terms of path integrals, right? So the trace of U E tau, I have shown just a few minutes ago, right, that this is the path integral for Euclidean position, right? In periodic, I'll indicate periodic by P. We know this is a closed, because this is E, right? This is a closed path of length tau, right? This is the length of the closed path of the exponential of 1 over h bar S E Q E. Right, so I just have to calculate this path integral. And the same for the numerator here, right? The trace means that, right? Means I take all the possible states at edges, so it's also the same path integral. But now instead of the operator here, I have a function, a classical function, tau, which is defined by the eigenvalues of this guy, right? When you working on proving this relation, you see that eventually I'll have these operators. I'll just write this as an integral between two states, make the borders of the states the same, and then integrate over them. But in the slicing, eventually you have this A of QE, which must be specified at a time. I must say, of course, this now depends on QE of at some time, right? And this will act on moving frame states like this one, right? And then you get the function itself, right? Which is what shows up here, and same state here. It's the same as here. Huh? So that's what defines this. This is the usual thing for path integrals, but this is a good exercise showing these relations. The same I did up here, right? Same idea. Right? So now notice something, right? That's the first time it's actually clear that an observable will be defined by the division of two path integrals. This will be this. Let me put a little bit more space over this. Right? As per this relation. Which means that all these strange normalization factors that come out of the path integral. Remember, the path integral, even if this is quadratic and do the proper integral, there are some awkward normalization factors here, and they will be the same in both, right? So it's the first time we'll see these again and again, but it's the first time where it's clear that these guys do not matter, right? They'll go away here. So that's another advantage of doing things like this, right? It's clear that this goes away as a normalization. And just to remind ourselves, I can think of this expectation value of the operator in terms of two systems, right? I can think of it as a quantum system of in contact with a thermal bath, so it's a quantum particle with this action in contact with a thermal bath at temperature h bar over tau Boltzmann constant, right? And tau is encoded here, right? So this is a period of length tau, right? So I have periodic conditions for the path integral. Or I can think of a system of classical objects in a chain of length tau and temperature h bar, essentially. Right? There's always Boltzmann constant there. Right? It's the same, would lead to the same thermodynamics. Now, how can I use this, right? The thing I want is usually this, in a quantum field theory course. So for now we're in quantum mechanics, but we'll get to fields soon enough. Right? And I want zero temperature, right? So what happens, how do I get back to TQ going to zero, right? How do I do that? Well, just have to look here and see what can you change, right? You can change the periodic conditions on these path integrals. And to get TQ to zero, I have to get tau to infinity, right? Which also means get beta to infinity, because this is 1 over beta essentially, right? So what I do is this, right? Beta is h bar tau. Huh? So what happens? The trace of this Euclidean evolution operator, which I have shown at the start, can be written in terms of minus tau over h bar energy, right, will be projected on the state of the lowest energy. Right? You see, I'm taking the temperature to 0, and what happens here at this evolution in Euclidean time is that as tau goes to infinity, right, this exponential of tau over h bar E0 is much, much bigger than the exponential of tau over h bar E1, right? Because E0 is bigger than E1, and I'm making the exponential huge, right? I mean, tau is huge. That means that those exponentials are all going to 0, but this one goes faster than this one, much faster, because now I'm taking E1 that is bigger than E0 and multiplying by a big number. So I can basically, and that's true also for the second excited state and so on, right? So the whole sum here is dominated by its first term. All the others I can forget. That means that this trace which was a sum over n, will now be dominated by only the lowest lying state. Right? All the rest of the sum don't matter, right? And the same happens here. If I take this quantity that goes into the numerator of the expectation value for A, right, I would also have a sum over states with A and U here. But now the sum goes away because this is dominated by the vacuum, right? So you have, again, U acting on these states. This exponential goes outside. And I have the expectation value of A in the vacuum of the theory, which is by definition the lowest lying states, the lowest lying state on the system, right? The state with the least amount of energy. So see, it all works out. The moment I take temperature to 0, I'm removing as much energy as I can from the system, right? And this sum is dominated by the lowest lying state, and I get essentially the expectation value in vacuum, right? So now this, what I'm showing is that this is the same as this with beta going to infinity or tau going to infinity or temperature going to 0. It's all the same thing. It's all the same thing. And I can use this to obtain a lot of observables that I want in vacuum, right? So important concept to remember that sending the temperature to 0 projects into the vacuum states of the theory. Right? So let's think of one of the green functions that we have been calculating, right? The endpoint functions. Think of the propagator we defined before between T1, T2 and T1, right? As this. I actually didn't prove that this guy is the same as this, but let's suppose I'm calculating this guy on the right, for now, which we know is the 2-point function that I defined clearly. This is in Minkowski space. Let's see what happens if I rotate. So now I'm thinking that I have some Minkowski time here, and I'm making the analytic continuation to the complex plane. So now this is the real part of t, this is the imaginary part of t, right? I have t1 and t2 somewhere here. I don't care too much where, right? And as I said before, I'm rotating in this direction. So tau 1, which is the Vicky rotation of t1, lives here somewhere, and tau 2 lives here somewhere, right? And there's a total period, right, that I'm taking these over a limited time. So these are intermediate times, but I'm saying I'm going from vacuum to vacuum, and I can set a distance in time from one vacuum to the other. So there's a period tau in this Euclidean space here, right, which I'm calculating the path integral over, right? This is the period which will give me the temperature, right? So this is directly related to the temperature I want to calculate this in, right? So the first thing I can obtain is this quantity, right? This is the expectation value of a product of two operators applied at times tau 1 and tau 2, right? I'll try to get back to that by using the procedure as shown above. But this I know how to calculate. This is periodic space, so it doesn't matter really which order I put here, right? And I'm doing this over beta, right? Which goes again into the periodic condition. So this is encoded here, right? This is where this periodic condition will be encoded, and this is path integral in Euclidean coordinates. Just like I did with the A above, right? Now, if I want to go back to Minkowski time, all I have to do is tau 1 goes into IT1, tau 2 goes into IT2. But as I go back, I have to see how they're positioned here, because in Euclidean time it doesn't matter because it's periodic, but in Minkowski it does. But you see that the rotation back solves this, right? If this was ordered in one way, I would go back to T1 before T2, and if they were ordered in another way, I would go back always to the time ordered product, right? So you always go back to the time ordered product in Minkowski space. Right? That's also true for if you put more than 3 fields there, then you could also do some ordering here, which is cyclic but very similar to the time ordering. So if I do this, then I get the time ordered product of Q then T1, Q of T2, right, at temperature beta, and if I want the zero temperature one, I just have to take beta going to infinity, which means the temperature goes to 0, and this guy becomes the object I want. So this is schematically the path you could take to to get the 2-point function you usually want. Some people actually prefer this path a lot. You could be thinking, what? But if I have already calculated this guy, right? Some, I mean, we have seen this for the forced harmonic oscillator, and you did it all in Minkowski space, right? Some people, especially the more axiomatic you are, the more danger you see in path integrals in Minkowski space, right? That I won't go into, but it is true that path integrals are better defined in Euclidean space. Of course, this is a bit of nitpicking, right? If you have a well-defined algorithm to calculate stuff, that it's good enough for me. It's good enough for most physicists. But if you want to really delve into the mathematics of this, the Euclidean one is more well defined. But then you exchange the problem of doing the path integral, which you can always do in Euclidean space, by the problem of Wick rotation, which is not always well defined. So in any case, you have a problem. From the practical point of view, I'll show in a moment or two that sometimes it's easier doing in Euclidean times because you can avoid, again, the Feynman prescription. We'll see that by doing things in Euclidean time and then going back, you go away from the poles that were in the real axis, and when you come back, there's no ambiguity on how you should circulate the poles. So again, we go back to that question we discussed a lot in the last video, which is how to avoid those poles and have a well-defined inverse of that delta minus 1 function. This is the green function, by the way. This guy is delta Feynman, right? So let's take a look at how can we see that. Think first of the free harmonic oscillator, right? So we had this operator we wanted to invert, right? Delta minus 1, which was this del 2 del t2 plus omega square, right? And then there was acting into a delta, and you wanted a delta function of t minus some type t prime, right? This is derivating in t, and you had that relation. If you go to Euclidean time, right, you have to rotate this guy, right? You have 2 powers of I in the denominator, so you end up with minus del 2 del t Euclidean square plus omega square, which will act, let's call for now, since I'm talking about the free oscillator, Euclidean delta for the free oscillator, which depends on 2 Euclidean times. Let's call Euclidean 1 and Euclidean 2. Of course, this derivative is acting on one of them. Let's take Euclidean 1, and this is delta t E1 t E2. But in the Euclidean time, this is periodic. The space, the Euclidean space here is periodic with period tau equal to h bar beta. And now we can forget about h again. I was keeping h around to see how h is really the temperature of quantum mechanics, right? It's controlling the quantum oscillations, and you see the analogs with temperature of a chain of classical objects. But now we can forget about H bar again and go back to our usual notation. And that means that I mean, the fact that this is periodic means that I have to solve this equation for periodic conditions. So delta free at T plus minus beta is equal to delta free of Euclidean, right? And one can prove that there's only one solution to that equation for this time, this interval of time belonging between 0 and beta, which is the cyclic condition, right? And that solution, that's a good exercise, is showing that this is the only solution, and the solution is this. I won't do it in details here. 1 over 2 omega 1 plus eta. I'll just tell what eta is in a second. Exponential of minus omega t Euclidean plus eta of omega t Euclidean. And eta of omega is actually the Bose-Einstein distribution, which indicates, for the first time we're dealing with bosons here, but so far this will be just a coincidence for us, right? What it is important for us here is that when I take temperature to 0, right? So when I go to 0 temperature here, which means beta goes to infinity, right? Eta of omega goes to 0, and the free propagators goes to that delta F we have figured out before, which is over 2 omega. Right? We're going back to Minkowski space, so undo Wick rotation, and I get to the exponential minus I omega t over 2 omega, which once again, if you compare with what we had before, right? In my notes, it's equation 37.3. This is very similar to that expression we had, which was this one. Right? This is delta S, and this T is because I took this guy to 0, right? So I'm looking only at positive time and comparing it to 0. See what happened here. I got the same propagator without prescription. You remember, to get to this, I had to be very careful about how I would go around poles and whatnot. So I'm basically avoiding Feynman prescription here, but again, you see that that's related with projecting with it in the vacuum of the theory. This time I'm doing it by taking the temperature to 0. So that's again another incarnation of the same idea. And finally, let's take a quick look at the forced harmonic oscillator. I'll be quick about this one because by now nobody wants to hear about harmonic oscillators anymore. You're probably eager to get to fields. So very quickly, what happens if I look at a forced harmonic oscillator in Euclidean space? So this was the action of the forced harmonic oscillator, if I do a Wick rotation, I'll just make these changes, which are the same I just made for the free harmonic oscillator. I'll do the same I did for, do the same for the source that I did for the coordinates, right? So I just define a Euclidean source, the derivatives get a sign, and then I can write minus the Euclidean action like this, right? It's just putting all the substitutions in there, you get this expression. So then I have to calculate the partition function, or the generating functional, which is given by this path integral. Remember that now that I am in Euclidean space, I have periodic boundary conditions. So there is a period here that is tau or beta, right? The beta, they are related, and now that I'm taking h bar equal 1, they are actually the same. And I'll suppress the Euclidean notation from down here because it's too cumbersome. And what do I have to do to get the answer to this path integral? I have to do integration by parts here and get the operator, right? I have to put all derivatives in the middle, right? But now I don't have the subtlety that I had in Minkowski space. Why? Because these integrals are all with periodic boundary conditions. So all these coordinates should be the same at tau 1 and tau 1 plus beta. Same here. So there's no subtlety when I do the integration by parts. The two edges here are actually the same point, so they will subtract and disappear. So first thing to notice is that on Euclidean space, I don't have to be careful with boundary conditions. They are periodic and they solve themselves. Then to go from here to here, right, I take tau 1 going to minus infinity in these limits, and tau 1 plus beta going to plus infinity, in a way that beta is going to infinity, and I'm projecting this into the vacuum. And then I can invert the operator easily. It's the same thing I did before, and get this propagator. So this is the propagator for the Euclidean space. So the first thing to notice is no singularities in the path of integration, right? I could use P here, so be careful when comparing with the Euclidean. Here I call this variable energy, but that's the same as P, which was just P0 in the previous time we looked at the forced harmonic oscillator. Right? So now no singularities, which is amazing. Actually, the singularities are in the imaginary axis, right? If I take an analytic extension of this guy, the poles are there, but they are in the imaginary axis, which doesn't seem like a problem until you remember that physics happens in Minkowski space. And I have to go back if I want to compare this with I had before and with nature. I have to go back to Minkowski space. So I have to Wick rotate back to Minkowski space. And how do I do that? Right? So we know how to rotate time. This is the expression right here. And now we want to rotate their conjugate momenta to time, which is energy, right? And there's ambiguity in choice here, and I'll do it in a way to keep this product the same, right? And the advantage of doing this is that waves propagating, you see, when we don't have any other coordinate, but once we go to field theory, you see that waves propagating towards positive time, Minkowski time, will also propagate towards positive Euclidean time, which is convenient, right? We don't want these two things to go in opposite directions. So if I rotate energy in a way to keep this invariant, it's better. So that means that rotating time and Euclidean time in this way will be equivalent of rotating energy in this way. And there's a difference in sign here. But now I have to be careful, right? I'm saying this rotation is actually a continual analytical continuation, and I cannot go all the way to the imaginary axis because there's poles in the imaginary axis. That's why I'm using like almost IE, right? I cannot rotate the full 90 degrees into the imaginary axis. I have to stop before getting to the poles. That means that my rotation will be almost pi over 2. So I'm going from the real Euclidean energy into the imaginary Euclidean, which will be the Minkowski energy, the real energy. But I have to stop just epsilon before getting there, right? I have to avoid this pole, right? That means that the relation between energy and Euclidean energy will be this one. I'm subtracting epsilon, I'm not going the full 2 pi. Right? I can invert this relation here and then expand this exponential. This epsilon is not the same here, but it doesn't matter, it's just a small real number and positive. Right? If I take this definition for the Euclidean energy and plug here, and also change in the integral and take care of all the powers of I up there, what do I get, right? So I had this Euclidean propagator, I make this substitution here, and I get this expression, which is the same Feynman propagator that I had before, right? But before I got to this, especially this denominator here, I got this by the prescription, the Feynman prescription. But again, see what's happening here. I'm projecting into a vacuum. I took the zero temperature limit in an Euclidean space calculation, which is projecting into the vacuum. And I'm avoiding these poles again by the only way possible, right? I have to rotate in this way because I want to preserve this. I don't want to get to the poles, so because I cannot, it's not analytical over there. I have to stop before I get again the Feynman prescription. So see, this Feynman prescription is very closely connected with going to a vacuum transition, because remember, this is periodic, now with infinite period. So again, I have a vacuum in a far off distant future, vacuum in the past, distant past, and that led me to Feynman prescription once again, which is the message of the day, right? So I think that's all for today, and we're finally done with quantum mechanics, and we'll get to fields next video. See you then.